this paper was put forth. And moreover, this paper enabled an integration between Mitiq, this quantum error mitigation toolkit I will speak about in this talk mainly, together with another software in Python that is used for gate set tomography. So basically to characterize noisy gates in a quantum computer. And likely here you see a similar integration in which Mitiq, used for error mitigation, was interfaced with a compiler called Biscuit, developed mainly at Berkeley Lab, which is a compiler that reduces 2-qubit gate counts to make programs more robust against noise, which affects more heavily multi-qubit gates. So this is a sort of like a broad overview of the work we've done, both at the software level, but also with research output. And I would like to especially point out this recent result together with the University of Chicago on code distance scaling. So this is an application of quantum error mitigation to quantum error correcting codes. Okay, so now let me really start the proper, more research and software-oriented part of the talk. We're gonna focus in this talk on noisy intermediate scale quantum computing devices. They're also called with their acronym NISQ. They actually resemble the first computers, as you can see from this photograph from the Colossus mainframe in the 1940s. There are very few available quantum computers worldwide, especially if we compare them to commercial electronics. They're generally sort of like bulky, even if the processor can be, and generally is, very small. The whole set of operations, fridges in some cases, and classical control electronics, it's quite cumbersome, and they require expert operators. At the same time, these NISQ devices has also modern features, because increasing number of them are connected to the cloud. So they don't only live in research experimental labs, but they're also connected to the cloud. And sometimes also for free, they can be accessed. We have a blog post about this, how to access for free cloud quantum computers on the Unitary Fund blog, which I encourage you to check out. They work with open source software at many levels, as you may see by having a look at the projects participating to Unitary Hack. There's really now toolkits doing a broad variety of things and specific things, from compilation to simulation to error mitigation and so on and so forth. And they can be accessed using the existing UX/UI web stack that has been developed over the past 50 years. So NISQ quantum computers are a strange hybrid because they're both very old, resemble very old computers, but also inserted in a very modern network. So let's see at the very high level, what does it entail running programs on quantum computers? So in its simplest form, a quantum program can be represented as a quantum circuit. So here you see 2 qubits that are then manipulated with a single qubit operation and a 2-qubit so-called control not X operation. There's also like more complex types of programs that plug these quantum circuits into a hybrid classical computing part, and they're used especially for these VQA applications, variational quantum algorithms. So then we have our quantum computer. Here you can see a Lego version. And through the cloud, we can send the quantum circuit instruction to the quantum computer. This instruction is then made executable for the quantum computer, And what is returned to the user is generally bit strings for each run. So in this case, you see many bit strings because I'm supposing that instead of having just 2 qubits, there is more qubits that have been involved in the quantum circuit and which were available on the quantum computer. And then using these statistics, one calculates an expectation value, which is the result of the operation. So from a theoretical point of view, this would imply having the evolution of the quantum system rho according to a noiseless and perfect Hamiltonian, which is the composition of these gates in terms of a unitary. So this is the ideal von Neumann master equation, which is just the master equation counterpart of the very famous Schrödinger equation for states. What happens in reality, though, is that this ideal, so-called noiseless Hamiltonian, cannot be implemented due to the presence of leaks and decay that you see exemplified here in a very simple model of an atom, which could have 2 levels inserted inside a cavity. So in a very general framework of cavity quantum electrodynamics, you can imagine your quantum computer and quantum processing unit as being composed of many qubits. Each qubit could be thought of as a 2-level system, generally interacting with a cavity. And here you see with gamma and kappa, you see quantified decay rays of both the cavity degree of freedom and the qubit degree of freedom. So these decay rates insert some noise, and at some point this signal will fade out. That's why at this point quantum computers are not yet at the level of usefulness, because at some point the signal just decays and we're not able to implement operations, programs that require many operations. So at some point one can imagine to obtain just something that's like white noise, like when you turn on an old TV, you're not able to reach any specific signal. And one very simple way to describe in a more general context of open quantum system what is happening, where the openness is the fact that there is some information and some energy leaking out, is with addition to this closed system evolution of a noise operator or super operator with a dimensionless coupling lambda that tunes its strength. So at lambda equals to 0, we have an ideal quantum evolution with no noise and leaks. With lambda greater than 0, let's say lambda equal to 1, we have a noisy operation. So generally, this is the context at which we are operating with quantum computers. Looking more closely what this entails, what noise actually means, well, this could be decoherence noise. That means that the signal just decays. Control noise, meaning that the operations that here you see shown on the block sphere are not perfectly instructed. So there is some mismatch between the pulses that are sent to the quantum processing unit and actually those that are implemented. In this case, this is sort of like an imperfect but coherent noise, because it can be expressed at the Hamiltonian level. There is also crosstalk noise, which means here, for example, you could see some ions trapped in some electromagnetic trap, which are then addressed with pulses. These could be ions or neutral atoms. And here, by this graphical depiction, you see the idea of when addressing a single qubit, you're actually also perturbing nearby qubits. This also happens in superconducting circuits, actually, and it's one of the main source of errors in those superconducting systems. There could also be pulse-shaped noise. This could be classical or quantum. And finally, there's also like leakage noise. So depending on the system, you may lose your qubit and your excitation. So your two-level system may not be completely closed. You may have intermediate levels, and you could also have more levels in a wider ladder. This sometimes is a bug that is used as a feature, but this all adds to the complexity of manipulating these quantum systems. So at the gate level, usually noise in quantum programs is simulated with can be simulated with random Pauli error. At the quantum channel level, which is a bit more general, one can also have models for decoherence, dephasing, erasure. And some assumptions are that noise is usually independent among qubits, but as we've seen, for example, in the case of correlated noise, this is not always the case. It is usually simulated after a perfect gate, but this also could not be exactly the case. So correlation could happen both in time and space. And the ideal operation of a perfect gate and noise may not be separable. And this is why there is also specific toolkits such as QTIP, which is the quantum information processing component of the quantum toolbox in Python, QTIP, which allows, given a quantum circuit, to then really tune, I would say, almost any degree of freedom, here shown at the pulse level of interactions, with respect to any kind of model quantum processor. So this is an example of an open source toolkit in which we're able to simulate noise even at the pulse level compilation. So this is something to keep in mind that adds complexity to these models. And if you'd like to dive into QIP, we have a series of talks called Quantum Software Talks on the Unitary Fund YouTube channel. And this is a great presentation by Boxy Lee that goes much more into details about how you could get started with QIP to model any kind of quantum processor. Okay, this was a quite comprehensive introduction to noise in quantum computing. I will try to speed up a bit to give an overview of quantum error mitigation and then get more into details. So first of all, let me start from Mitiq itself. And in general, like, but this applies to all sort of error mitigation. So generally, as we've seen, there is a quantum program defined by a user that is run on some hardware, and then there is an expectation value that is obtained. The general idea of error mitigation, which we could also call approximate quantum error correction, is that instead of just generating a single quantum circuit, there is a sampling that is made on the back end in terms of intermediate circuits that help discover this noisy landscape that characterizes the quantum processing unit. And then, given that there is many quantum circuits, many quantum programs that are all different, that are sent to the machine, there is also different noisy results, and adopting some inference techniques that are generally completely classical and decoupled in application to the first part of quantum error mitigation, which is the quantum sampling, allow a user to obtain an error mitigated result. So this is a quite general framework that applies to most quantum error mitigation approaches. Another important thing to mention about quantum error mitigation and the techniques that I will give an overview about is that quantum error mitigation is a field that has recently emerged also as a keyword, but actually key concepts exist in many of these adjacent fields, such as open quantum systems, quantum error correction itself with the use of symmetries, variational quantum algorithm, quantum optimal control, as well as quantum characterization, verification, and validation, also known by its acronym QCVV. Okay, so now let's give a brief overview of quantum error mitigation techniques, the most common ones: zero-noise extrapolation, probabilistic error cancellation, and so on and so forth. So zero-noise extrapolation is the one I will focus mostly with the rest of the talk. And it's based on the idea of scaling noise at the full quantum circuit level, which you see here from an image from IBM paper. So I will delve into these techniques. I will not speak too much about it at this point. Let me give a brief overview of other techniques. Probabilistic error cancellation and quasi-probabilistic representation work at the noisy gate level representation level. So you can imagine that in ideal quantum program, as it's been discussed previously, you may have a unitary that is a composition of ideal gates. But actually what happens is that on the quantum processor, we are applying a noisy unitary. Imagine that it's provided by this operator here. So with the standard development of this relation, one could reconstruct the ideal quantum operation in terms of a linear combination of the noisy ones, with these coefficients here, that then whose weight, overall weight, it's referred as negativity, and it's sort of a cost that one needs to pay in the noisy landscape in terms of sampling overhead in order to reconstruct the ideal representation. Then there are so-called learning-based methods in which one trains data using a simulator, generally that simplifies the original quantum program in terms by substituting gates that are hard to simulate on classical computers. For example, substituting non-Clifford gates with Clifford gates, learning to correct the output based on the noisy simulator in a classical computer, and then transposing this model to the actual quantum program that is then run on the real quantum computer, and then predicting from the noisy results the error mitigated results. Then there is another technique called, well, many names. It goes from virtual distillation to subspace expansion. I call these symmetry-based techniques. And the key feature is that the noisy state is reprojected. So here I'm trying to grasp the most salient features of these techniques. So imagine that your final state psi should be invariant with respect to application to this operator MS, which could be a stabilizer or a more generic operator. So what happens if we measure all these, let's say, symmetry operators on a noisy state raw, not the ideal state? Well, what happens is that we can obtain a symmetrized operator, density matrix, sorry, rho S, which is just the result of this projection in a part of a space that we know should be devoid of errors in this wider system. And finally, let me also mention that there is also techniques such as dynamical decoupling and randomized compiling. These are techniques that work mostly, or let's say, yeah, they work at the compilation level. So you see here a quantum circuit in which here with these rectangles, we are showing XY sequences that were not present in the original quantum circuit. And these sequences are introduced in order to decouple qubits that otherwise would stay idle from noise. This is actually a very old technique that actually has been proposed also with other names beyond quantum computing in NMR, and can be it's been first explored at the pulse level, and here you see it's an abstraction at the gate level. Polytwiddling also works, as you see here graphically, in terms of a quantum circuit that it's modified from the original one into a quantum circuit that has some additional gates, as you see here in these fainter colors. And these additional gates are introduced in order to randomize the noise in a way that then it's easier to correct. So polytwiddling is also called randomized compiling. And there's also other research approaches. So this is just a summary of some relevant papers, but of course the quantum error mitigation literature is growing by the day, and this is by no means a comprehensive list. I also point you to these two reviews, one by Suguru Endu and collaborators, published in 2021, and one by Zhenyu Kai and collaborators, which actually, I believe it's been published in Review of Modern Physics, I believe. Or in any case, it's at this archive link. And you can find all of these references at mitiq.readthedocs.io, which is the documentation for this Python toolkit that I'm gonna speak about. Okay, let's get into more detail about zero noise extrapolation with Mitiq. And zero noise extrapolation is the first technique that I mentioned in the summary slide, and which I'm gonna give more theoretical context about. Before delving into zero noise extrapolation with Mitiq, let me give a summary of the Mitiq project here. So Mitiq can be used with a simple command line instruction, pip install Mitiq, and this will install Mitiq from the PyPy server. You can find more details and contribute to the project on GitHub. There is a paper published in Quantum that contains all information about the background theory and details about the software implementation. And especially I would like to point out that the documentation, it's really comprehensive. There's over 20 tutorials, there is a full API doc, and also a user guide that is helpful to explore the different techniques that are implemented in Mitiq. And we have weekly community calls on Friday at 9 AM Pacific time. I'm sorry, this is India Standard Time. It's quite late in the evening. And we've tried to alternate times for community calls, but if there's more requests to hold them at different times, please do reach out to us. It's just been a bit tricky to coordinate with everyone from Pacific time to Eastern time to Central European time. And there's also Quantum Wednesday, which is sort of like a journal club or open coding session that we have on Wednesdays. It's not just devoted to Mitiq, but it's also more generally an opportunity to review other papers about quantum error mitigation or discuss coding ideas with respect to quantum error mitigation. I would like to acknowledge once again the fact that the Mitiq project that has grown so much was first established thanks to DOE funding. Okay, let me try to speed up a bit, because if I want to provide time for questions, I think I need to speed up a bit. So here you see how the different techniques are represented in terms of modules in this framework of the quantum sampling and the inference with the Mitiq. So here, for example, you see that for zero-noise extrapolation, you have Mitiq.zne.scaling the first part and Mitiq.zne.inference as the second part. And in terms of compatibility, Mitiq works with most front ends, any backend, because it's backend agnostic. And then what one obtains is then an error mitigated value, as you see here, that should approach the ideal value of 1, for example, for a benchmark case. So we also have a lot of benchmark circuits that one can run to test if the technique is working as expected for the given problem of choice or for a new quantum error mitigation technique. This once again a summary of existing techniques implemented in Mitiq. So beyond zero-noise extrapolation, there is also probabilistic error cancellation, Clifford data regression, digital dynamical decoupling, and readout error mitigation. And there's also a bunch of tutorials, as I've mentioned, on the Mitiq user guide. So let me give here really a quick overview of how zero-noise extrapolation works. So as we mentioned previously, this noise operator at lambda equal 1 is what happens actually on the device. But what if we increase artificially the noise of a system? Well, you may think, why should someone make things worse? And the reason is to have more data points to sample from, to then try to fit the zero noise value. And in the first proposal, this noise amplification was made by so-called pulse stretching, meaning that the pulse giving the same instructions would be operated at the attenuated intensity for a longer time, meaning that proportional to the background noise, it would have a more feeble effect. But and this is like some results from the IBM paper that showed this. I will just go quickly here. And this pulse stretching actually is not always implementable on all quantum processors. And what was done in this paper with some collaborators from the Unitary Fund team was to implement ways to do this stretching at the gate level. And here you see two so-called local and global folding, whose meaning you can immediately understand. In this case, you just insert single gates as duplicates. So instead of having just the gate G, one insert G dagger and G. And the property of these gates is that, unitary gates, is that G dagger G is equal to the identity. So at the logical level, this quantum sequence, which is much longer, does the same as this quantum sequence, and the same applies here. So then when with these more sampling data points, when one can obtain the zero noise expectation. So here you see really a couple of lines of code in which a QIQT quantum circuit with a H gate and C naught is then folded with a scale factor of 3. And then here you see the folding that is applied to bigger noise scale factor, and then it's used to extrapolate the zero noise limit. So this part is actually inaccessible for noise level from 1 to 0, but it's actually estimated, inferred, thanks to this other sampling. And this is, in this case, an exponential fit. Is actually data from an IBM Q Armonk device over a randomized benchmarking circuit. And Mitiq allows one to use several kinds of extrapolation, not only of folding, And these are at the so-called factory level. So not only one can have exponential fits, but also linear fit or Richardson fit and other kind of also adaptive fits that here you see benchmarked on different hardware to see how they compare. And in this case, as in the previous case, we knew that for this benchmark, which is a randomized circuit, 2-qubit randomized benchmarking circuit, the ideal value is 1 in case of zero noise. And so we're able then to estimate how different models perform on different hardware. I believe that, unfortunately, my time is up, even if I would have spoken much more. So I believe that now it could be a nice time to wrap up if there are questions. So let me mention that here is a list of papers that not only cite Mitiq, but also use Mitiq in research. Mostly, as you can see from these papers, it's for time evolution of quantum systems. For example, in this case, a plaquette model was implemented on a quantum computer for quantum field theory simulation, and the results were improved by the use of zero noise extrapolation. Here is also a list of researchers and various institutions that use Mitiq to advance their research. I think I don't have time really to go into further details with respect to the other research topics. So maybe I can stop here and ask if there are questions. If there are no questions, I can just take the rest of the time and continue with the presentation.
I have two questions. Can you hear me?
Please. Yes.
Okay. So thank you for your talk. So you have enlisted noise mechanisms, but in one of your slides. So, but I did not see thermal noise, vacuum noise part of that list. So question is, any reasons why they are not part of noise list?
Oh, it was just a brief summary. So the techniques that I've shown here for error mitigation can work with different types of noise. Some techniques are more effective with respect to a given type of noise, subset of noise, and some others in a more general sense. So yeah, there is no specific reason that I didn't cite also the kind of noise that you referred to.
Second question is where one can read in more details math and physics behind these noises, because it will help to introduce them in the Lindblad equation intelligently.
So you're asking for some references with respect to these noise models?
Yes, but because it will help to introduce them in the Lindblad equation.
Yeah, so the equation I've shown is a general equation that also includes the Lindblad model. So the equation in which you see the ideal operation and then also the noise operator, these, for example, could be a Lindblad superoperator. And in terms of resources with a practical application, I can refer you to the QTip.org documentation that has a very clear explanation of how this noise can be simulated with Lindblad superoperators, with equivalent Monte Carlo quantum trajectory methods, as well as more general master equations that include non-Markovian effects.
Thank you. I have one more question. Sorry. How to verify the output results after introducing noise mechanisms? Because Hamiltonian or system becomes non-conservative.
So if I understand correctly, your question is how to verify that
I'm getting correct results, because when the system is conservative, I can check total energy at any time of evolution of the system, or I can check the commutation relations, whether it is satisfied by the output results or not. So in case of non-conservative like Hamiltonian, in that case, how can I verify the output result?
So generally what, as you mentioned, you could use some observables and track them in time to see how they evolve even under the action of a non-conservative Hamiltonian would be a non-Hermitian Hamiltonian, if I understand your question. So this would be equivalent to having an open quantum model in which you have some sort of leakage and decoherence. So one way we not only check the time evolution of a system under the effect of noise, but also how quantum error mitigation, so these strategies to counteract noise are effective, is through benchmark quantum circuits, which you can imagine as sequences of unitary gates that can also be modeled as time-dependent Hamiltonians, of course, of which we know exactly the final state result. So if in a randomized benchmarking sequence, for example, you apply sequences of XY, XY, XY gates with an even sequence, you will return to the initial state. For example, if your initial quantum register was in the 000 state, you will return to that state. And so then you can measure an observable with respect to this initial state, which could be just the probability of having it excited or not. And you know that, as it was shown in these previous plots, you expect here to measure from 0, rho 0, where rho is the final state, you expect to measure 1. So there's a different benchmarking quantum sequence that one can use. This is just one of them, the one randomized benchmarking circuits. There's also so-called mirror circuits that also play with this idea of the application of unitaries and then the transpose of the unitaries. And then there's also other kinds of quantum circuits, such as similarly GHZ states that are applied and then reversed, and so on and so forth. And actually, you can find these in Mitiq. So here I can show you real quick. Yeah, welcome. Here, if you go to the Mitiq documentation and you go to the API doc, you see that the first section is benchmarks. And here you see these different sort of quantum circuits, which can be modeled as Hamiltonians. And you see you have mirror circuits, randomized benchmarking circuits, GHZ circuits, quantum value circuits, quantum phase estimation circuits, W state circuits. So these are examples of circuits whose output is sort of like controlled in the ideal case. So that then when they're executed on a noisy, either simulator, for example, with QTIP, or actual device, how the end result differs from the ideal one can give you a test of what is happening in the dynamics.
Mm-hmm. So these benchmarks will help me to understand whether the modeled like system which I'm modeling goes correct or not. So
Exactly.
okay, so there is no rigorous commutation relations which can be evaluated and checked in a dynamic sense. So only these benchmarks will help me to understand whether the behavior of my system is correct or not.
I'm not sure I fully understand the question of these commutation relations, but let me put it into other way. Okay, yeah, sorry. If you want to expand, yes, please.
No. Commutation relations means when the system is conservative, then you have boson commutation relations, you have commutation relations for fermions. So these are the like basic things I can check whether these commutation relations are satisfied or not during time.
Yeah, but you can always, so if you expand the commutation relation, in the end, you're always measuring it against a given state. So you can always recast this problem in terms of an execution of a quantum program in which the commutator part, or each part of a commutator is run. So you run different quantum circuit in which you swap the gates, and these act as the commutator. And then for each quantum circuit, you measure several instances of a measurement. And so you're able for any circuit to check the commutator relation of a given Hamiltonian. So let's say that you start from the zero state, you apply X, the equivalent of, let's say, XMP, and then you measure against the zero state. And then in another quantum circuit, you start from the zero state and you apply P and X, and then you measure. So this could be formalized. And another thing I want to mention is that it's true what you say, that if you are actually really interested into checking the noise model underlying your system, tools like gate set tomography may allow you to do it at the gate levels. You may want to reconstruct the noisy operation. So this is not really in the error mitigation part, but is more in the noise characterization part.
Thank you.
Welcome.
Thank you.
Are there any more questions from the audience? Or if you are unable to speak, just type it in the chat box. See the chat box myself, but see it. I guess there are no questions.
I have a question.
Yeah, please go ahead, Lava.
So so we are extrapolating here the zero noise extrapolation you are saying. So why are we doing this? Like, do we want to see how the system dynamics changes if there is no noise at all, or is it like we are removing the noise, unwanted noise, something is present?
Yeah, we're trying to remove the impact of noise in terms of errors on the calculation, and reconstructing or better inferring the expectation value that one would have obtained from an ideal time evolution, which means an ideal quantum program.
Okay. So these errors are due to like the circuit design, like in that, due to that, or why this error comes up?
So the errors occur because we're not able to run exactly the gates, and so to say, exactly the Hamiltonian that one would like. And so this is the reason why these errors occur, because noise is unavoidable, and quantum error correction strategies cannot yet be implemented at scale because of a qubit overhead that they would require in the first place to be implemented. So this inference is used to try to reconstruct what would happen if there was no noise.
Okay.
And since noise cannot be removed, one can do is to learn how the noise impacts the computation in order to learning how it impacts the computation at different level of noise, different kinds of computation, in order to then guess, so to say, extract the zero noise value. Some of these estimators are unbiased. For example, for the probabilistic error correction technique, which I didn't, error cancellation technique, which I didn't delve into, but they come at the price of an overhead in sampling.
Okay. So we are checking, suppose if we remove these errors and how actually the system works, suppose if, I mean, so computationally, like we are simulating how the actual system dynamics happen if we remove this error. That's what are we trying to find out here?
Yes, we're trying to do that,
Okay.
but we're not able to
Remove.
simulate the full dynamics.
Okay.
The only thing that we are able to do is to extract, let's say, the final value. Although one could say that if you measure at each point in the dynamics, then you're basically reconstructing also the ideal dynamics.
Okay.
Yes, but that's what you're trying to do.
So, okay, this is our inability to simulate the actual system.
Exactly.
So
Yeah.
so what are the possible errors? We are trying to remove those errors in order to get like almost ideal system dynamics. What it happens.
Exactly. Yeah.
Okay. So that's it. The simulations will be, the simulator is like in QTIP. Is it so? Like whatever.
So the simulation can happen with several software. It can also happen, for example, in QIQT, you have some so-called fake devices that represent actual devices and to which you can add noise. This also can be done with CIRC and also with other sort of like front-end tools. And as you say, you can also do it in QTIP.
Okay. Okay.
But then you would use Mitiq to remove these errors in mitigation.
Okay. Thank you so much.
Welcome.
Okay, so I guess we have to start the next talk also, and we had good amount of discussion. So let us thank Dr. Nathan Shammah for this introduction to this Mitiq and telling us more about it. So thank you very much.
Excuse me, ma'am.
Yeah.